So today we're talking about dividing and graphing complex numbers. We kind of call this our quadratic leftovers. Stuff we haven't quite done yet, but all needs to be done. So to divide complex numbers, we use what's called the complex conjugate. If we have a complex number a plus bi, the complex conjugate is a minus bi. And what happens when I multiply a plus bi times a minus bi is I get negative b squared I squared, and I get negative abi, and I get positive abi, and I get a squared. And so what happens is I end up with a squared plus b squared, because remember, I squared equals negative 1. And so now this is real. And that's the important part, because we cannot have imaginary numbers in a denominator. So if I have 3i divided by 2 plus 4i, I'm going to multiply the denominator and the numerator by the complex conjugate of the denominator. So 2 minus 4i. And our fraction rules apply. Whatever I do to the bottom, I have to do to the top. And then we'll use what we learned about multiplying to simplify this. So 3i times 2, 3i times 2 is 6i, and 3i times negative 4 is minus 12i squared. And then in the denominator, I get 2 times 2 is 4, and I get minus 8i, and then I get plus 8i, and I get minus 16i squared. And remember, I squared equals negative 1. So I get 6i minus plus 12, because negative 12 times negative 1 is positive 12. And in the bottom, the negative 8i and plus 8i are 0. So I get 4 plus 16, because negative 16 times negative 1 is positive 16. So I get 12 plus 6i over 20. And I can divide these all by a common factor of 2. So I get 6 plus 3i over 10. And I leave it like that. Or you can write it as 6/10 plus 3i over 10. And then 6/10 reduces to 3/5 plus 3i over 10. Multiple choice options might have it separated, and we've seen it separated like that on SAT and CASP questions. So let's do another one. So let's write this down. To divide complex numbers, we multiply the numerator and the denominator by the complex conjugate of the denominator. Just like we can't have a radical in the denominator, but we can have one in the numerator. We can't have imaginary numbers in the denominator, but we can in the numerator. So here's another example. 3 minus 5i divided by 1 plus I. So my complex conjugate of the denominator is 1 minus I. We changed the sign on the imaginary term only. Okay, so 1 minus I. And then we multiply it out. 3 times 1 is 3. 3 times negative 1 is negative 3i. Negative 5 times 1 is negative 5i. Sorry, negative 5i times 1 is negative 5i. And negative 5i times negative I is plus 5i squared. And then in the denominator, I get 1 times 1 is 1. And 1 times negative I is minus I. And I times 1 is plus I. And then I times negative I is negative I squared. So remember, we're just doing the outside, the first, the outside, the inside, and the last on both of them. And then I can combine some like terms. 3 minus 8i plus 5i squared. Remember, we're going to replace that I squared with negative 1. And 1 minus I squared here. Okay, and so that's 3 and negative 5i squared, or positive 5i squared, is 5 times negative 1. So that's minus 5. minus 8i, that's my numerator, which becomes negative 2 minus 8i. And then that's 1 minus negative 1, so that becomes plus, so my denominator is 2. And then I can divide everything, negative 1 minus 4i, because I can divide them both by 2. So graphing complex numbers is just like graphing ordered pairs. We turn the x-axis into our real axis, and we turn our y-axis into the imaginaries. And notice I've added i's to all of the numbers along here. So we have positive i's are up and negative i's are down. So when we're graphing the point 4 minus 3i, we go over to the positive 4 in the real, and we go down to negative 3i, and there's our point 4 minus 3i. It's like graphing 4 comma negative 3. And so if I have negative 2i, that means I'm not going over at all. I'm just going down to negative 2i on the y-axis, the imaginary axis. And then if I have negative 5 plus 7i, it's over negative 5 and up 7i. So negative 5 plus 7i. So it's just like the point negative 5 comma 7. This is like the point 0, negative 2. So they're really easy to graph. We just think of the x-axis as the real axis and the y-axis as imaginary. The last thing we're going to talk about is raising I to powers. We said that I is equal to the square root of negative 1. And we've already looked at the fact that when I square that, the square root goes away and I get I equals negative 1. I squared equals negative 1. Now what if I get I cubed? I cubed is I times I squared. Does that not give us cubed? And so that's this I times a negative 1. So I cubed is equal to negative I. Okay. And then I to the 4th is equal to I squared times I squared, which is negative 1 times negative 1, it equals 1. And then what you're going to notice, if I go to I to the 5th, I can say that's I times I to the 4th, which is just I, because I to the 4th equals 1. If I go to I 6th, it's I squared times I to the 4th. So that's the same as I squared, because I to the 4th, anytime I have I to the 4th in there, that equals 1. And so that's negative 1. And I to the 7th is I cubed times I to the 4th, which is negative I. I cubed is negative I times 1, which is negative I. And we have this pattern. It repeats. I to the 4th times I to the 4th is 1 again. So we get I equals I. I squared equals negative 1. I cubed equals negative I. And I to the 4th equals 1. And then it cycles around. I to the 5th. I to the 6th, I to the 7th is the same thing. I to the 8th, I to the 9th, I to the 10th, I to the 11th, I to the 12th. Every 4, we get back to our circle of it equaling 1. So we can use that to find higher values. If I want I to the 35th power, well, I can figure out how many I to the 4ths I have in there, and then the leftover will tell me whether it's I squared, or I cubed. And if I don't have any leftovers, it equals 1. So we can take 35 and divide it into 4, because that's our pattern. Our pattern repeats at 4. And so 4 goes into 35 8 times. 8 times 4 is 32. And then I get a remainder of 3. So that means I go through this cycle 8 times, and I end up at I cubed. So I to the 35th power is equal to negative I. Okay, these are our values, but everything's going to equal one of those things. So I to the 35th equals negative I, because my remainder was 3, and so that's, I end up at I cubed. How about I to the 125th? Well, again, we're going to divide 4 into 125. 4 goes into 12 3 times. I get 0, bring down the 5. 4 goes into 5 once. So I go through this pattern 31 times, and I have 1 remainder. So I end up here at I to the first power, which is equal to I. So when we are asked to do I of higher powers, we divide by 4, and then we take that remainder and figure out whether it's squared, cubed, fourth, or first power. So if I have I to the 300th power, I don't have to keep writing the pattern out. I do 300, 4 goes into 300, 4 goes into 30, 7 times, that's 28. And then that's 20, so 5, remainder 0. Well, remainder 0 means it goes in 4 times. It goes in evenly, so this is equal to 1. Okay, so we divide by 4. We divide exponent by 4. And then use the remainder to determine what it equals. And it's one of those things.